Hi and welcome back to Gaffy's Grinds. This is video number 2 in our organic chemistry series on thermal chemistry. The usual reminders, guys, if you're just joining us now, these videos are designed to be watched in order. It's going to be much harder to understand if you jump in here and you don't do number 1 first. So go back to video number 1 if you're just joining us and do that video number 1, thermal chemistry. The videos are designed in small chunks. Small, manageable, understandable chunks with lots of practice after each one. It's really important that you do the practice, you give it your best shot, okay, from memory, and see how you got on, and then check with the answers that I put up. If you're not going to do the exercises and the questions, you're not going to learn very much from watching these videos, so you're pretty much wasting your time. So really important that you do the tasks, okay. Try and eliminate any distractions. Just get rid of the phone for the half an hour unless you're using it to watch this, and then try and put it on do not disturb or something that's going to stop any notifications coming in and distracting you. Okay, we'll jump into it. So we are talking about exothermic and endothermic reactions. In the previous video, we discussed how energy can move between a system, which is basically reacting chemicals, and the environment of the system, which could be the container of the system or the space around the container. So we talked about how energy can move in between those two things, from the system to the surroundings and from the surroundings to the system. We also discussed how matter can move from the system to the surroundings and from the surroundings to the system. So this whole section is going to be about how energy moves from between those two places. So let's have a quick look at an example. So if we take an example of, we'll say we have some wood. We have a few logs here on there. Okay, so we're going to build a campfire. So we have some logs. This is wood. Okay, and we want to get the wood burning. Well, before we get the wood burning, we're going to measure the temperature. So say we've got our thermometer. We're going to measure the temperature, and we'll say the starting temperature. Starting temp is equal to, say, around 23 degrees. That's generally, summertime when you're out camping, air temperature is going to be around 23 degrees. Now, we want to get the fire started. What are we going to need? Well, we're going to need ourselves a match. Okay, a match will help us to get the fire started. Well, why do we need a match? Why won't the fire just start by itself? Well, this is the energy we have to put in to get the reaction started. Now, if you have previously studied rates of reaction in Leaving Cert Organic Chemistry, then you should know what this particular type of energy is called, the energy required to get the reaction started. Speak the answer on 3 if you know it. 1, 2, 3. Okay. If you said activation energy, well done. If not, if you didn't know that or you haven't studied that before, that's what we call, that's the energy required to start the reaction, is the activation energy. And every single reaction out there has an activation energy, an energy required to get the reaction started. Okay. So we have our wood, our fuel, and starting temperature is 23 degrees. And we're going to use our match. We're going to get our fire started. And this is an example of what we call a combustion reaction. Example, this is a combustion reaction. Combustion just means burning. And we should be very familiar with that from our previous topics on organic chemistry when we looked at fuels. So combustion, it means to burn. Okay, so this is a combustion reaction. Now, what we know is going to happen is that when we combust, what's going to happen is, well, our logs, after we get it started, after we add the activation energy, our logs are going to catch fire. So here's our fire. Okay, and in this particular case, this is a chemical reaction, a combustion reaction. What's going to happen is energy is going to be transferred from the system, which is the burning wood, the system, to the surroundings. So lots of energy is released or transferred. I like the word transferred rather than lost, or transferred into the surroundings. So in this case, the fire or the wood is the system, and the air around, or whatever, it could be your sitting room if you're lighting a fire in the sitting room, it could be a campsite if you're lighting a fire in a camp, then that is your surroundings. Okay. Now, what is going to happen to with our thermometer? We're going to take our thermometer again, and remember, thermometer is for measuring temperature. So we're going to take our thermometer, and what will have happened to it before and after? That's our thermometer. Well, we're going to have a final temperature. Okay, now we might not be able to predict an exact number, but tell me, is it going to be higher or lower than the starting temperature? Tell me now. 1, 2, 3. Okay, well, it's going to be higher, okay, because heat is being, or energy is being transferred to the surroundings. So the final temperature of the surroundings is going to have gone up. So the final temperature is going to be equal to, we'll say 43 degrees. So say it's gone up by 20 degrees. It's heated the surroundings by 20 degrees. Now, I don't know why this is not drawing as good as it normally does. I apologize about this. There we go, that's better. Okay, final temperature, 43 degrees. Okay, so I'm just gonna have to pause the video. Give me 1 second. Okay, apologies about that. I just had to make more space for myself above my drawing here. Okay, so this is a combustion reaction. We take a fuel, we burn it, and energy is transferred to the surroundings. How do we know energy is transferred to the surroundings? Well, the temperature of the surroundings has increased. It's gone from 23 degrees up to 43 degrees. And anytime you burn things, this is what happens. The temperature of the surroundings increases because energy is released or transferred to the surroundings. We have a specific name for this type of reaction, okay, or process. We say, so this is a type of process, we would say it's any type of process or reaction, because this is a reaction, and in chemistry we're usually talking about reactions. Any type of process or reaction which causes the temperature of the surroundings to increase. Okay, that's what we're talking about here. A reaction which causes the temperature of the surroundings to increase. We call this an exothermic process. Exothermic reaction or exothermic process. We have a special name for these types of processes or reactions. Now, why do I say process or reaction? Well, this is a chemical reaction. There are chemicals, bonds are being broken, atoms are reforming into new products. So this is a chemical reaction. But other things could also happen, processes like if I take an ice cube and I melt it. There's no chemical reaction there, that's a process, melting, but energy is still moving. Okay, so the ice cube is, well, actually, energy is going to be going into the ice cube. So that one doesn't really isn't really going to be this exothermic process. It's going to be a different type of process. But energy is still able to move, even though it's not a chemical reaction. That's why I'm using the word process. Okay. So anyway, I'm going to get rid of the word process. Sorry, and I'm just going to highlight exothermic because that's the word I want us to focus on. Exothermic. Okay. So we say that this process is exothermic. Damn, what the? Come on. Sorry about that. I don't know why that's not going into a nice rectangle for me. Anyway, sorry about that's not working. Okay, now what about the words here? Let's break it down. So like we usually do, we're going to break it down into its parts. Exothermic. So I'm going to take this word thermic, and we had this similar to this word in the previous video. It comes from the word thermal. Thermal. And the word thermal comes from the word heat energy. The phrase heat energy. So thermal refers to heat energy. So exothermic, something to do with heat energy. Okay. The word exo, well, that comes from a different word. That comes from the word to exit. Exit. And exit means leave. If you exit somewhere, you leave it. So exothermic heat energy leaves. Okay, now where does it leave? Where does it go to? Well, it leaves and it goes to the surroundings. So it leaves and it moves, shown by the arrows, showing movement. Energy moves to the surroundings. So from the system to the surroundings. Okay, so system, which is the reaction mixture or the chemicals, to the surroundings. That's what we're talking about for exothermic. And we know because the temperature goes down, okay, or the temperature goes up, sorry, the temperature of the surrounding goes up, which means heat energy has moved into the surroundings. Very quickly, if we were to just draw, if we take a look at this again, the before and after of the combustion reaction, if we were to represent using these boxes, the energy stores. If we were to say that this is the energy of the system, energy of the system at the start of the reaction here is high. There's a lot of energy in the system. And if we were to draw a second store, and if we were to say that this one represents, sorry, I need this to form a box. If we were to say that this box represents the energy of the surroundings, then we would say the energy is quite low. Not empty, still some energy there, otherwise, you know, it'd be much colder than 23 degrees, but it's not empty, but it's not really full either. Okay, and then if we look at the stores again after the reaction, so the energy of the system, well, what's happened to the energy of the system as the fuel gets burned? Well, as the fuel gets burned, the energy reduces, it goes down, it's less energy. And what's happened to the energy of the surroundings? The energy of the surroundings, well, we know that energy has left the system and moved it to the surroundings. So the energy of the surroundings compared to what it was before will have increased. So there will be more energy in there. So we see energy increased. And the energy of the system will have decreased for this particular type of reaction. Okay, it's time to do some questions, some practice now. Okay, so what I want you to do is, as usual, from memory. So without, if you were taking loads of notes, while I was speaking there, I prefer if you didn't, because it's better to actually listen, try and understand what I'm saying, and then do the practice. Okay, so trying to do this from memory, so completing these sentences from memory, it should be pretty straightforward. Okay, so I'm going to let you have a go at them now, please. Okay, so you should only be watching the video if you have paused the video and tried to complete the sentences, just filling in the gaps. Okay, so hopefully those were pretty straightforward. There was a couple of them there where it referred to stuff you learned in the previous video, and we're always trying to get retrieval practice into your revision, retrieving things from previous lessons. It's the best way of making sure you remember it for the long term. Okay, so an exothermic reaction, the energy of the reacting system. So the system is the chemicals, or the actual reacting chemicals. What happens to it? Now, if you weren't really sure what that was getting at, well, we're talking about, does it go up or down? So we're going to use the word increases or decreases there. So if you weren't able to do that already the first time, maybe pause the video and decide now, does it increase or decrease? Okay, so you should be watching the video now if you have had a go at that. In an exothermic reaction, the energy of the reactant system decreases. Okay, so it goes down. So the energy of the reactant system decreases. What about B? Exothermic reactions cause the temperature of the surroundings to do what? So what happens to the temperature of the surroundings? So if you weren't sure what I was getting at there, I hope you were. If you got this already, great. If not, again, we're talking about, does the temperature increase or decrease the temperature of the surroundings? So if you weren't already able to do that, pause and then do it now. Hopefully you said exothermic reactions cause the temperature of the surroundings to increase would be correct there. Well done. A thermometer measures what? It's pretty straightforward revision. A thermometer measures temperature. The symbol for heat energy is, this was from the previous lesson, hoping that you wrote capital H. The symbol for a change in heat is, again, previous video, we learned this. It's delta, which is the triangle. It's the Greek symbol for change, delta, and heat is the capital H, so it's delta H. In an exothermic reaction, energy is transferred, something the reacting system, something the surroundings. Okay, so it will be from the reactant system to the surroundings. Okay. Oh, I suppose you probably weren't able to answer the last one. Okay, so I forgot to actually tell you about that. So that's another thing I have to tell you up here. Okay, so any exothermic is any type of process or reaction which causes the temperature of the surroundings to increase. Okay, so what we're going to say about the delta H, this guy, delta H. Delta H means the change in heat. When we're talking about delta H's, we're referring to heat energy of the system. The heat energy of the system. So delta H can be positive or it can be negative. Positive or negative. So this will be delta H plus or delta H minus. Now there will be a string of numbers that comes after this depending on the type of reaction, but the numbers will either have a negative sign before them or a positive sign before them, or they might have no sign before them, which means positive. Okay, so sometimes if things are like, we don't always go around writing +2, plus, you know, how many people are there? Oh, there's +7 people there. We don't really always write pluses. In maths, we usually only put a sign in front if it's a negative number, because the standard is for most things to be positive. Okay. Now, what does this mean? Well, delta H positive means the system has more energy at the end. Delta H negative means the system has less energy at the end of the reaction. Now, if we go back down here, this is what we had before. The system decreased in energy for an exothermic process because the energy was released to the environment or to the surroundings. So the system's energy actually decreased from the start to the finish. So if delta H is negative, that means there's less energy left in the system at the end. Then this is exothermic. So this is how you will know that the reaction is exothermic. So exothermic, delta H is negative. I really want you to think about why it's negative, because that's a better way of trying to remember it than just learning off delta H is negative for exothermic reaction. It's negative because there is less energy in the system at the end. There's negative amount of energy in the system at the end. Where did the energy go? If there's less there now than there was at the start, where is it gone? Well, it was released or transferred to the surroundings. So that's why it's negative, because there's less energy there in the reaction mixture at the end. So it had to have gone somewhere. The only place it can go is to the surroundings. So that means it released the energy to the surroundings. So delta H is negative. Okay, so now you should be able to answer G. Okay, so hopefully if that wasn't enough time, pause the video and do it now. Okay, so delta H for an exothermic reaction is what? Well, it's negative is the correct answer there. Okay, so I'm going to put these answers up here. Okay, and you guys can pause the video and make any corrections that you need to do now, please. Okay, now that is the exothermic reactions. We're going to look at another type of reaction now. Okay, so I need to make some more space here. Okay. Now, in the previous video, we talked about the chemical reaction of an ice pack. So we have an ice pack. And it's one of those ice packs that you squeeze. So inside is a bag, and outside is a bag. And when you squeeze, you burst the bag. Okay, and inside the bag is the chemical water. Outside the bag, or inside the big bag, but outside the little bag, is a chemical called ammonium chloride. I'm just going to draw, it's a powder chemical. It's called ammonium chloride. Now, just say for instance, we're going to do the same reaction. We're going to eliminate the ice pack. We're going to eliminate the bags, and we'll just do it in the lab. So we're going to take a beaker, and in the beaker, we're going to put, oh, that's not what I wanted to do. Oops, sorry about that now. So inside the beaker, we're going to put H2O, the liquid water. And we're going to put in our thermometer to check the temperature. So we've got a system, we've got our water, we've got a beaker, and we've got our thermometer. And we're going to add to that, we're going to add this same chemical that's in the ice pack. We're going to dissolve some of this powdered substance called ammonium chloride. Ammonium chloride. We're going to add that in, and we're going to give it a stir, we're going to dissolve it. And our thermometer is going to measure the temperature for us. This is starting temperature. And we're going to imagine that the starting temperature is 23 degrees. Okay, so the starting temperature is 23 degrees. What's going to happen? Well, after a while, we know what happens in the ice pack. Once we squeeze the bag and we mix the chemicals, the ice pack gets cold. Gets cold to touch. Well, why is it cold to touch? Well, if we take a look what's happening in our reaction down here, we've got we've still got our water. We've got H2O. We've got our thermometer. And we've got our ammonium chloride is now dissolved. Well, the reason why it's cold is because heat energy, instead of being given out like it did when we burned the wood, heat energy is taken in from the surroundings. So heat energy moves from the surroundings, this time into the container, into the system. So from the start to the finish, the system has extra energy that it's taken in from the surroundings. So we say that energy is transferred from surroundings to the system. So energy is transferred from the surroundings to the system, and this causes the temperature to go down. Okay, so this causes the temperature to go down. Why does the temperature go down in the thermometer? Well, if you think about it, the thermometer is also surroundings. So if we look at the thermometer, it's sitting in this reacting mixture. Here's our water and our reacting mixture. As well as energy coming from the surroundings, which we're thinking about as the air around the container, heat energy is also drawn away from the thermometer. And that makes the thermometer get colder. That's why the temperature goes down. So the thermometer counts as part of the environment, of the surroundings. In the previous example, maybe I didn't make that clear, the thermometer counts as the surroundings. So energy is moving from the system into the thermometer. And that's what's causing the temperature to go up. Okay, so it's because the thermometer counts as the surroundings, energy is taken away from the thermometer and it goes down. Okay, so this is what the example we've looked at is dissolving, or is, an ice pack. An ice pack. Or dissolving ammonium chloride in water. That's what's happening inside an ice pack. That's our example. And what type of process or reaction is this? Well, just like before, it's any process or reaction which causes the temperature of the surroundings, to decrease, because it's taken in energy from the surroundings. The temperature of the surroundings decreases. So that's what we're talking about here. Any process or reaction which causes the temperature of the surroundings to decrease. We call these endothermic. Use the word endothermic. Again, the thermic bit comes from thermal, which refers to heat energy, same as before. The endo bit, well, endo comes from the word in. And the word in means to enter. So we say heat enters the system from the surroundings. So from the surroundings, this time heat enters the system. This is endothermic. And for endothermic, that means overall the system's energy increases as the reaction happens. So the system's energy increases, which means the change in H, delta H, is positive. The system has extra energy that it took from the surroundings. So delta H will be positive. That is how we can identify. That is one way we can identify it's an endothermic reaction if delta H is positive, or if the temperatures of the surroundings have decreased, then we know it's an endothermic process. If we just go back down quickly and have a quick look at the energy stores like we did before, we have our container, which we're saying is this is energy of the system. In the beginning, the energy of the system is quite low before the reaction occurs. And at the end, the energy of the system is higher. It's taken in energy. We say the energy of the system has increased. What about the energy of the surroundings? Well, we know about temperature change. The energy of the surroundings, sorry, all those boxes are supposed to be the same size, by the way. I know they probably don't look it, but they're supposed to be. It's quite hard to draw on this. So the energy of the surroundings in the beginning was high. So you use this when you want to cool something down. So when something's got a lot of energy, it's hot. So you've got inflammation in your hand if you've banged it, or what am I saying? Energy of surrounding. So this is when your skin gets hot. If you get a bang, you want to remove the heat from the surroundings. Your hand is the surroundings. The ice pack is the system. So the energy of the surroundings will cool down. If it cools down, that means the energy of the surroundings has decreased. Surroundings decreased. Okay, all right. I think you're ready to answer some more questions. So let's do our second set of questions here. Number 2. Okay, so pause the video and try and complete them to the best of your ability, please. All right, well done. I'm hoping that you managed to do those okay. They're similar to the first set. Here are the answers. I'll let you go through them yourself. Pause the video and go through them. Okay, all right. Just another little bit of new stuff now. What we're going to do is we're going to make a quick table of examples of exo and endothermic reactions. Okay, so we're going to have exothermic examples. And we're going to have endothermic examples. Just so that we're aware there's more than just one or two. In general, most reactions that exist in the world are going to be exothermic processes. Most reactions release heat, but not all. Obviously, the first one we've seen is combustion. And this is a very, very common reaction, combustion reaction. And we have anytime we burn a fuel, basically, all of those, that chapter on fuels that we were talking about, when we burn any of those fuels, we get a combustion reaction. and that is going to be exothermic, which releases energy to the surroundings. Very useful and important reaction to civilization. Another type of reaction, if you've studied acids and bases already, or if you've done volumetric analysis, you've talked about neutralizations. Neutralization. So on 3, speaking to the screen, what is a neutralization chemical reaction? Okay, should have said a neutralization is where we mix an acid plus a base, and it gives us salt plus water. Well done if you said that. Neutralization, acid plus base gives you salt plus water. All right, so there's 2 examples of exothermic reactions, and overall, if we look at the thermometer, what happens to the thermometer as the reaction occurs? Well, in the beginning, they're low, and in the end, they are higher. So the temperature of the surroundings will increase. So the temperature will be higher. Okay, increases. What about exothermic? Well, a classic example of exothermic is actually the process of photosynthesis. So any of us who study biology will know that photosynthesis happens in the leaf of a plant. So I'm drawing a leaf, and we know that energy is absorbed by the leaf for photosynthesis. So energy travels from the surroundings into the system. So the leaf is the system, and we take in light energy from the sun, which is basically outside of the leaf is the surroundings. So energy travels from the surroundings to the system, and the chemical reaction or process that happens inside the chloroplast is able to use the light's energy to make starch. Okay, so that is a classic example of an endothermic reaction. Another endothermic reaction is the one we looked at, dissolving ammonium chloride in water, and we find this in ice packs. That is a classic endothermic reaction. Another example is cooking an egg. Where we have a frying pan and we have our egg, which I'm just going to color just for fun. So we have our egg, our yolk of our egg, and underneath we have our heat source. And for the egg to cook, energy is taken in. Okay, so energy is taken in to the egg from the surroundings. So that is another example of an endothermic reaction. If we were to look at the thermometer here, say the temperature of the surroundings in the beginning would be quite high. Sorry. Yeah, the temperature of the surroundings, would be quite high while it's heating. And if we will look at the thermometer again at the end, we say the temperature of the surroundings would have decreased because energy is going to be taken in. So if we think of the ice pack, you put it on first when the inflammation is high and your hand is very hot. Apologies. Hand is very hot. When you put your ice pack on for a while, the temperature is going to decrease. Okay, so temperature is going to decrease. Now, it's question time. So we're going to do set number 3 now. Okay, so you have to state whether each of the following reactions are exothermic or endothermic. Okay. Part G is quite challenging. Have a little think about it, and E and G, sorry, are both quite challenging. Have a little think about it, and we'll discuss them afterwards. So pause the video, try the questions now. Okay, here are the answers. You should only be looking at them now if you've tried them. So A, burning a candle, any burning is always exothermic. Heat is going to be released. Dynamite being detonated to blast rocks, obviously that's a hell of a lot of energy being released in dynamite, and it is a combustion, so it's exothermic. A leaf photosynthesizing, well, it's taking energy from the surroundings to make food, so that's endothermic. Coal burning, it's another combustion, that is also exothermic. Evaporating water, so water turning from well, you tell me, what is evaporation? What is evaporation? On 3, say the answer to the screen. 1, 2, 3. Okay, I'm hoping that you said evaporation is turning from a liquid to a gas. Okay, that's what evaporation is. Now, what happens to the temperature? Think about it. What happens to the temperature when we evaporate something? Hoping you're saying, well, if going from a liquid to a gas, if I take water and I turn it to a gas, I've got to increase the temperature. So if the temperature, and I've got to take energy in to make it happen, basically. I've got to take energy in from the surroundings to make it happen. So that is going to be endothermic. So if if you put water in a glass or in a saucepan, the more heat you add to it, the more heat it can take in, the quicker it's going to happen. It's a little bit counterintuitive, that one. Respiration in mitochondria. Well, if you study biology, you'll know that respiration releases energy to the cells. So the whole idea there is it's an exothermic reaction. It's a highly exothermic reaction. You can break down glucose and sugars and release a lot of energy by doing it. So it's exothermic. And G, a very challenging one, but it's exothermic. Is freezing. Exothermic gives out heat. What? It actually is, though, exothermic, if you think about it. Let me just, I have to think about this myself because it is quite a challenging one. How's the best way to explain it? Freezing. So if you're taking liquid water and you're turning it into solid, so you have to remove heat from it to get it to freeze, it has to get colder. So energy has to leave it. Okay, so if you think about it, you've got water, you want to turn it into a solid, you have to remove energy from it to decrease its temperature. And by doing that, well, where's the energy being removed to? It's been removed to the surroundings. So it has to be exothermic. If it's going, energy's going to the surroundings, it has to be removed. It's a tough one. That's a challenging one. Okay, don't worry too much if that's puzzling you. It's a cold, something that's so cold as ice. You think of ice, you think there's no way it can be exothermic, but making ice actually is exothermic. Okay, so, and actually, if you ever touch a freezer, it can be quite hot. If you've got an ice cream maker, when you touch it, if you've got one of those ice cream makers, you know, that you put the mixes in and they spin around. If you ever touch them, they're quite hot. So actually, that's probably a good. I might use that example the next time I'm teaching. Right. We've got one more set of questions for you guys to do now. You have to identify whether the following reactions are exothermic or endothermic based on the value for delta H for the reaction. Okay, so I'm just going to highlight a few things here. Identify whether they are exothermic. So I'm highlighting what you need to do. You need to identify. Sorry, my highlighter is not working here. Not sure why. Apologies. Just. Excuse me now, just give me a second. Sorry, I can't get my highlighter working, so I'll have to do without it. So it says identify whether the following reactions are exothermic or endothermic based on the value for delta H for the reaction. So the key thing here is you've got to look at delta H. And specifically, you really can ignore the numbers for now. We're going to look at what the numbers mean later on in future videos. But for now, you can ignore the numbers and identify if it's positive or negative. Okay, so without looking back, I don't want to go back and find out which one is positive and which one is negative now. I want you to actually try and do it from memory, figure out which one is positive and which one is negative, and really think it through. Why would it be positive? Why would it be negative? Okay, once you've done that, then I want you to classify each of these reactions as endothermic or exothermic. Okay, so pause the video and try that now. Okay, so I'm hoping that you were able to do that, and you saw that in the first reaction, we have the combustion of methane. It's CH4 plus 2 O2s. Okay, so it's combustion because we're mixing a fuel with oxygen, and it's giving you a delta H of minus 890. Now that means that the change as the reaction happened is negative. There's less energy in the products now than there was in the reactants. There's less energy. So where did the energy go? It was released to the surroundings. So if it's minus, it's exothermic. So minus 890 is exothermic. So A is exothermic. And if you were able to answer them, then I'm pretty sure you're going to be able to answer the rest of them. If you weren't able to answer that first one, and now you have it, you should be able to do the rest. Pause now and do them. Okay, and here are the answers. So A is exothermic, B is endothermic because it's positive, C is endothermic because it's positive, D is exothermic because it's negative, E is endothermic because it's positive, and F is exothermic because it's a negative number. All right, that's it for today. You now know what exo and endothermic reactions are. To summarize, what can we say specifically about an exothermic reaction? So speak your answer to the screen. What things do we know about an exothermic reaction? Okay, I'm hoping that you said exothermic reactions. Well, first of all, they have a delta H, which is negative. Oh, you should mention that. They cause a temperature change in the surroundings. They cause the temperature to increase of the surroundings. And they release heat is another way of saying it. So they release heat, or they cause the temperature of the surroundings to go up, and they have a delta H, which is negative. Examples then are combustion reactions, neutralization reactions. What about endothermic? Let's summarize that now. What do we say about endothermic? Summarize it there, speak your answer out. Okay, I'm hoping that you said endothermic has a delta H which is positive. The word endo means in, which means energy goes in or takes in from the surroundings. It's a process or a reaction which causes the temperature of the surroundings to decrease because energy is taken in, or energy is transferred from the surroundings to the system. Okay. Examples of endothermic are ice packs, or dissolving ammonium chloride in water, which is what happens inside an ice pack. Frying an egg would be another example. And photosynthesis is a really, really important example. All right, guys, that's us finished. A really important idea there of what endo and exothermic reactions are. So I'm hoping that you found it okay. If you didn't, I suggest you go back and watch parts of the video again that you're struggling with. And I'll see you in the next video.